Septembre 1942, Evansville Shipyard, Indiana. Andrew Jackson Higgins stood in the middle of a cornfield 400 miles from the nearest ocean and made a promise that every shipbuilding engineer in America said was impossible. We will build landing ships in 72 hours, not 72 days, not 72 weeks. 72 hours, from the moment steel touched the slipway until the ship slides into the water. The engineers laughed. The Navy officers shook their heads. The established East Coast shipyards sent telegrams calling it a publicity stunt. But Higgins was not joking. He had seen something that changed everything, and the man who showed it to him was a year-old welder from New Orleans named Marcus Henderson, who had just revolutionized ship construction with a technique so radical that traditional shipbuilders called it insane. What none of them knew yet was that Henderson's prefabrication method would not just build ships faster. It would make the D-Day invasion possible. It would enable every amphibious landing in the Pacific. It would allow America to put armies on hostile shores faster than any nation in history. And it all started because one welder refused to build ships the way ships had been built for 200 years. The crisis was already critical by summer 1942. America had been at war for 9 months. The disasters were piling up. The Philippines had fallen, Singapore had fallen, the Japanese controlled the Pacific, the Germans controlled Europe, and America's ability to strike back depended entirely on one type of vessel that did not exist in sufficient numbers: the landing ship tank, or LST. The LST was ugly, ungainly, and absolutely essential. 328 feet long, 50 feet wide, flat-bottomed like a barge, with enormous bow doors that opened to discharge tanks and trucks directly onto beaches. It could carry 20 Sherman tanks, or 40 trucks, or 500 tons of cargo, plus 200 troops. It could cross oceans, land on any beach, unload in minutes, and sail away to do it again. British designers had created the basic concept after Dunkirk, when the evacuation of 338,000 troops demonstrated the desperate need for purpose-built landing craft. But British shipyards were overwhelmed building destroyers, corvettes, and merchant ships to replace loss from U-boat attacks. They could not build LSTs in the numbers required. The job fell to America. The original estimates were sobering. Using traditional shipbuilding methods, East Coast naval yards projected D to 2 months per LST from keel laying to launch. The Navy needed an 000 LSTs minimum. At D months per ship, even with multiple yards working simultaneously, it would take years to build the fleet. Years that the Allies did not have. Winston Churchill was already pressing for a cross-channel invasion. Stalin demanded a second front to relieve pressure on the Soviet Union. Admiral King wanted to go on the offensive in the Pacific. Every strategy required amphibious assaults. Every assault required LSTs. The shortage was strangling Allied strategy before it could begin. The Navy turned to an unlikely savior. Andrew Jackson Higgins, a New Orleans boat builder with a reputation for building small landing craft and an even bigger reputation for fighting with Navy bureaucrats. Higgins had already designed the LCVP, the Landing Craft Vehicle Personnel, the iconic Higgins boat that would carry troops onto D-Day beaches. But the LCVP was small, just 6 feet long, carrying 6 men or a jeep. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. The LST was D times larger, ocean-going, infinitely more complex. Traditional shipbuilders insisted LSTs had to be built in established naval yards using conventional methods: steel frames erected on slipways, hull plates riveted in place, compartments built piece by piece, engines installed late in construction, electrical systems wired manually. Painting and finishing work done in place. The process required armies of specialized workers and took months. Higgins looked at these methods and saw only waste. He had been building boats in swamps and rivers for 20 years. He understood something the naval architects did not. Ships did not have to be built on slipways. They could be built anywhere, in pieces, then assembled rapidly like giant erector sets. The key was prefabrication. But Higgins needed someone who understood both welding and manufacturing on an industrial scale. He needed someone who could translate his vision into reality. He found that person in Marcus Henderson. Henderson had spent Kine's years working in the petroleum industry in Louisiana. He welded pipeline, storage tanks, refinery equipment. He understood how to fabricate large steel structures quickly and efficiently. He knew that the secret was not faster welding or better welders. The secret was eliminating the work that did not need to be done. In traditional shipbuilding, workers built the ship where it sat. If a compartment needed a bulkhead, workers would measure, cut, position, and weld that bulkhead in place inside the cramped interior of the partially completed hull. If a deck needed support beams, workers would carry those beams through narrow passages, maneuver them into position, then weld them overhead. Every weld was difficult. Every piece was fitted individually. Every measurement had to account for the tolerances and variations that accumulated as construction progressed. It was slow, hard, and required highly skilled workers. Henderson saw immediately that this was backwards. Instead of building the ship in place, build the pieces first, then put the ship together. Prefabricate large sections in workshops where workers had room to move, light to see, and gravity working with them instead of against them. Weld bulkheads flat on the ground. Build deck sections complete with support beams, plumbing, and electrical conduit before installation. Fabricate entire compartments as modular units. Then lift these massive sections with cranes and join them together on the slipway. The concept was not entirely new. Some shipyards used limited prefabrication for certain components, but no one had proposed prefabricating an entire ship to the degree Henderson envisioned. The engineers said it would not work. Steel sections that large would warp and distort. The pieces would not fit together. The structural strength would be compromised. The welding would fail under stress. It was too radical, too risky, too different from proven methods. Henderson ignored them. In September 1942, he convinced Higgins to give him 3 weeks and a crew of 20 welders to prove the concept. They would prefabricate a complete LST bow section, 4 feet long, weighing 200 tons, assembled from modular pieces built in a temporary workshop. If the pieces fit together and the welds held, Higgins would commit to the prefabrication method for the entire production run. If Henderson failed, they would build LSTs the traditional way. Henderson's workshop was a cleared space next to the Higgins plant in New Orleans. No building, just a concrete pad, welding equipment, and stacks of steel plate. He divided his crew into specialized teams. One team cut steel plate to exact dimensions using templates Henderson designed. Another team built the frame sections. A third team assembled bulkheads and interior compartments. A fourth team handled the complex curves of the bow plating. The key innovation was Henderson's jig system. He built massive steel frameworks that held pieces in perfect alignment during welding. The jigs were essentially giant 3-dimensional patterns. Place the steel components in the jig, clamp them down, weld them together. Remove the completed section. The jig ensured that every section was identical and that all sections would fit together perfectly during final assembly. Henderson worked 20 hours in a day for 3 weeks, sleeping on a cot in the workshop. His welders matched his pace. They understood they were not just proving a concept, they were potentially changing the entire trajectory of the war. If prefabrication worked, America could build landing ships faster than anyone imagined. If it failed, thousands of soldiers would die on beaches waiting for equipment that arrived too late. En Octobre 3 1942, the test assembly began. A 50-ton crane lifted the first prefabricated section, the keel and bottom plating, and set it on a temporary slipway. Workers positioned it precisely using Henderson's alignment marks. Then the crane lifted the first side section, 40 feet long, complete with internal framing and 2 watertight compartments. The section weighed Trent 5 tons. Henderson, supervised as workers, guided the section into position. The alignment pins slid into their sockets. The welding flange met perfectly. There was no gap, no misalignment, no distortion. Exactly as Henderson had calculated. The welders made the final structural welds in 45 minutes. Then the crane lifted the opposite side section. Again, perfect alignment. The bow sections came next, the complex curves that veteran shipbuilders insisted could never be prefabricated fit together like puzzle pieces. By the end of the first day, the bow section was 60% complete. By the end of the second day, workers were installing the last internal compartments. On the third day, the completed bow section sat on the slipway, 4 feet of finished ship structure. Navy inspectors examined every weld, measured every dimension, tested the watertight integrity. They found nothing wrong. The prefabricated section met or exceeded every specification. The welds were actually superior to traditional in-place welding because Henderson's welders had worked in comfortable positions with proper lighting and easy access. The dimensional accuracy was better than conventional construction because the jigs eliminated human, measuring error. And the time savings was staggering. The bow section that would have taken 6 weeks to build using traditional methods had been completed in 3 days of assembly, plus 3 weeks of prefabrication that could be done simultaneously with other work. Andrew Jackson Higgins looked at the completed section and made his decision. "We are building every LST this way, full prefabrication. I want this ship in the water in 72 hours from keel laying." Henderson smiled. "We can do 60 hours if you give me enough cranes." The Navy was skeptical. Admiral Cochrane, responsible for amphibious warfare ship procurement, visited the Higgins plant in November 1942. He watched as Henderson's crews assembled a complete LST from prefabricated sections. The keel sections were laid on the slipway at 6 du matin on a Monday. By noon, the bottom plating was complete. By 6 de l'après-midi, both side sections were in place. By midnight, the bow and stern were attached. Tuesday saw the superstructure installed, the tank deck completed, the engine rooms fitted. By Tuesday night, the ship was recognizable as a vessel. Wednesday brought final welding, systems installation, and painting. At 2 de l'après-midi on Wednesday, just 56 hours after the keel touched the slipway, the LST slid into the water. Admiral Cochrane stood speechless. He had seen ships built. He had overseen naval construction for 20 years. He had never seen anything like this. Higgins was not finished impressing him. By January 1943, we will be launching 1 LST every 72 hours from this yard. By March, 1 every 48 hours. By summer, 1 every day. The Admiral thought Higgins was insane. No shipyard in the world had ever sustained that pace. But Higgins understood what the Admiral did not. Henderson's prefabrication method eliminated the bottleneck. In traditional shipbuilding, the slipway was the bottleneck. Only 1 ship could be built on each slipway at a time. Construction time determined production rate. But with prefabrication, the slipway became just an assembly point. While 1 ship was being assembled on the slipway, digs more were being prefabricated in workshops around the yard. Hundreds of workers could labor simultaneously on different ships, all out of each other's way, all working in optimal conditions. When 1 ship launched, the next ship's keel could be laid immediately because all the sections were already built and waiting. Higgins expanded the New Orleans operation, and then did something even more audacious. He built 7 more LST construction yards in locations no traditional shipbuilder would consider. Evansville, Indiana, Seneca, Illinois, Ambridge, Pennsylvania, all inland locations, hundreds of miles from the ocean. The established shipyards on the coasts screamed in protest. "You cannot build ocean-going ships in cornfields in Indiana. How will you get them to the ocean?" Higgins had already solved that problem. The LSTs would float down the Ohio River to the Mississippi River, then down the Mississippi to the Gulf of Mexico. Yes, the journey was 500 miles through river channels designed for barges and riverboats. Yes, there were dozens of railroad bridges with insufficient clearance. Yes, it seemed impossible. Henderson made it possible. He designed the LST superstructures to fold down, reducing the ship's height by 2 feet. The crew would collapse the superstructure before entering river channels, then raise it again upon reaching the Gulf. The folding mechanism added complexity to the prefabrication process, but Henderson's teams mastered it. By February 1943, LSTs were regularly making the journey from Indiana to the Gulf of Mexico. Farmers stood in their fields watching ocean-going warships float past cornfields. It was surreal, impossible, and it worked. The production numbers validated Henderson's method beyond any doubt. The Evansville shipyard built its first LST in 72 hours in January 1943. By March, they were launching one every 60 hours. By June, one every 40 hours. By September 1943, Evansville was completing one LST every 24 hours. One ship per day from a yard that did not exist before the war, in a city 400 miles from the nearest ocean. The other inland yards matched this pace. Seneca, Illinois, built LSTs on the Illinois River using Henderson's prefabrication system. Ambridge, Pennsylvania, built them on the Ohio River. Across all yards, American production of LSTs exploded. The Navy had projected needing 3 years to build 000 LSTs using traditional methods. Using Henderson's prefabrication system, America built 05 LSTs in just over 2 years, from 1942 to 1945. More importantly, the ships arrived in time. The invasion of North Africa in November 1942, Operation Torch, used the first LSTs built by traditional methods on the East Coast. Only Trent were available. The landings succeeded, but barely. Insufficient landing craft meant troops and equipment came ashore slowly, allowing German reinforcements time to establish defensive positions. By July 1943, when the Allies invaded Sicily, 200 LSTs were available. The landings were faster, more effective, more overwhelming. By June 1944, for the Normandy invasion, over 400 LSTs participated. The beaches were choked with landing craft. Tanks, trucks, artillery, and supplies poured ashore in unprecedented volume. The prefabricated LSTs made D-Day possible. In the Pacific, the impact was even more dramatic. Every island assault required LSTs. Tarawa, Kwajalein, Saipan, Guam, Peleliu, Iwo Jima, Okinawa. Each operation depended on landing ships, delivering marines and equipment directly onto hostile beaches under fire. The faster America built LSTs, the faster the island-hopping campaign advanced. The faster the campaign advanced, the sooner Japan faced defeat. Marcus Henderson never sought recognition. He remained in New Orleans throughout the war, supervising prefabrication operations and training other yards in his methods. He earned a modest salary, lived in a small house, drove a used truck. His name appeared on no awards, no citations, no official recognition. Andrew Jackson Higgins received the credit and deserved much of it. Higgins had the vision, the drive, and the willingness to fight Navy bureaucracy. But Henderson had the technical genius that made the vision real. Without Henderson's prefabrication system, Higgins' promise would have been impossible. The collaboration between the two men demonstrated something fundamental about innovation. Vision without implementation is just talk. Implementation without vision is just incremental improvement. True innovation requires both. Higgins provided the vision. Henderson provided the implementation. Together, they changed warfare. The technical details of Henderson's prefabrication system reveal why it worked so well, and why traditional shipbuilders had failed to develop similar methods. The key was not one innovation but a complete rethinking of the construction process. Henderson approached shipbuilding like manufacturing, not like artisan craftsmanship. He studied assembly line production, mass manufacturing techniques, and industrial efficiency methods. Then he applied these principles to structures weighing thousands of tons. The first principle was standardization. Every LST built using Henderson's method was identical to every other LST. Exactly identical, not similar, not approximately the same, but identical down to the millimeter. This was revolutionary in shipbuilding. Traditional naval construction allowed for variation. Each ship was slightly different because each was built by different workers using measurements and judgment. Every piece was cut using a template. Every frame was built in a jig. Every section was assembled using fixed patterns. Workers did not measure anything. They simply followed the jigs and templates. This had multiple advantages. First, skilled labor requirements. A worker with 2 weeks of training could cut steel plate to exact specifications using Henderson's templates. Traditional shipbuilding required workers with years of experience making complex measurements and cuts. Second, standardization ensured that prefabricated sections would fit together perfectly during final assembly. In traditional construction, workers constantly adjusted and modified pieces to make them fit because nothing was exactly the right size. Henderson's sections required no adjustment, they were already the right size. Third, standardization enabled mass production of components. Henderson could build D identical sections simultaneously, instead of building one section D times. The second principle was modularity. Henderson divided the LST into Trentwit major sections. The keel was 3 sections, each side was 5 sections. The bow was 4 sections. The stern was 3 sections. The tank deck was 7 sections. The superstructure was 5 sections. The engine rooms were 4 complete units. Each section was built as a complete module with all interior fittings, plumbing, electrical wiring, and equipment installed before the section left the fabrication workshop. This meant that workers installed interior components while standing on solid ground, with full lighting and easy access. Compare this to traditional construction, where workers installed components inside cramped, dark, partially completed space. The efficiency difference was enormous. A worker installing electrical conduit in Henderson's fabrication shop could work D times faster than a worker installing the same conduit inside a partially built ship. The third principle was parallel production. In traditional shipbuilding, construction was sequential. First, you built the keel, then you built the frames, then you installed the hull plating, then you built the decks, then you installed the equipment. Each step waited for the previous step to complete. Henderson made everything parallel. While one crew assembled the keel on the slipway, 20 other crews were building other sections in workshops around the yard. The bow sections were being built simultaneously with the stern sections, simultaneously with the deck sections, simultaneously with the superstructure sections. All these sections came together on the slipway in a carefully choreographed sequence that took hours instead of months. The fourth principle was crane-intensive assembly. Henderson designed the entire process around crane capacity. Every section was sized and weighted to be lifted by available cranes. The largest sections weighed 50 tons, within the capacity of the 75-ton cranes Higgins installed. Every section had lifting points built in. Every section was designed to be positioned precisely using crane hooks and guide cables. The traditional shipbuilding approach minimized crane use because cranes were expensive and required skilled operators. Henderson made cranes central to the process because crane time was cheaper than worker time. A crane could position a 40-ton section in D minutes. Workers manually positioning the same section would take days. The fifth principle was welding optimization. Henderson was a master welder, and he understood that welding productivity depended on position and access. Welding flat on the ground was fast and easy. Welding overhead in cramped space was slow and difficult. Henderson designed his sections to maximize flat position welding and minimize difficult position welding. In the fabrication shops, over 90% of all welding was performed in the flat position or horizontal position. Only the final assembly welds on the slipway required vertical or overhead welding, and these final welds were simple structural connections, not complex joints requiring multiple pass. A skilled welder could complete the final assembly welds on one major section in less than an hour. The sixth principle was workflow optimization. Henderson mapped every step of the fabrication process. He identified bottlenecks. He eliminated wasted motion. He arranged workshops to minimize material handling. Steel plate arriving at the yard went directly to cutting stations. Cut pieces went to forming stations where hydraulic presses bent them to shape. Formed pieces went to jig assembly stations. Completed sections went to staging areas near the slipway. Nothing moved unnecessarily. Nothing was handled twice. Preparing and narrating this story took us a lot of time, so if you are enjoying it, like this video, it means a lot to us. Now, back to the story. To implement these principles, Henderson created an entirely new organizational structure. Traditional shipyards organized workers by trade. All welders worked together. All pipefitters worked together. All electricians worked together. Foremen assigned workers to different locations around the ship as needed. This created chaos. Workers spent hours each day just moving between work locations. Tools and materials had to be transported to wherever the work was happening. Henderson organized workers by product, not by trade. Each major section had a dedicated team. The bow team included welders, pipefitters, electricians, and structural workers. This team built bow sections, nothing else. They worked in one location. Their tools stayed in that location. Their materials were delivered to that location. They built bow section after bow section, becoming incredibly efficient at their specific task. The tank deck team built tank decks. The engine room team built engine rooms. Each team developed specialized expertise. They knew every detail of their section. They identified improvements. They developed shortcuts. They became faster with every section they built. By the 6th section, a team was 3 times faster than on the first section. By the 50th section, they were 5 times faster. Henderson also revolutionized quality control. Traditional shipyards inspected completed work, finding defects late in the process when they were expensive to fix. Henderson built quality control into fabrication. Every jig had built-in inspection points. If a piece did not fit perfectly in the jig, it was wrong and was rejected immediately. This meant that by the time a section reached the slipway for final assembly, every piece had already been verified correct. The inspection process during final assembly became trivial. Inspectors simply verified that sections joined correctly and that final welds met specifications. They did not need to check thousands of individual components because those components had been checked during fabrication. This saved enormous amounts of time and prevented costly rework. The materials handling system Henderson designed was equally innovative. Traditional shipyards moved materials using trucks, forklifts, and manual labor. Materials often sat in storage yards waiting for workers to request them. Henderson created a continuous flow system. Steel plate arrived by rail. Cranes unloaded it directly onto cutting tables. Cut pieces moved to forming stations on roller conveyors. Formed pieces moved to jig stations on overhead cranes. Completed sections moved to the slipway on rail-mounted transporters. Material moved continuously in one direction, from raw steel to finished ship. The training system Henderson implemented was equally important. He could not rely on skilled shipbuilders because there were not enough of them. He had to train inexperienced workers quickly. He developed a training program that focused on repetition and specialization. New workers started with simple tasks: grinding welds, loading cutting tables, operating conveyors. As they gained experience, they moved to more complex tasks: operating cutting torches, running welding equipment, building sections in jigs. Within 6 weeks, A worker with no prior experience could perform most tasks in the fabrication shop. Within 3 months, they were fully productive. Within 6 months, they were training new workers. This rapid skill development was possible only because Henderson's system eliminated complexity. Workers did not need to understand shipbuilding. They needed to understand their specific task. The jigs and templates provided all the complexity. The workers provided the labor. The scheduling system Henderson created was perhaps his most sophisticated achievement, coordinating 38 major sections, each built by a different team, each requiring precise timing to arrive at the slipway exactly when needed, was a logistics nightmare. Henderson solved it with a system that looks remarkably modern, similar to just-in-time manufacturing developed decades later by Japanese automakers. Each section had a production schedule that worked backwards from the final assembly date. If the keel was scheduled to be laid on Monday at 6 du matin, then the first keel section had to be complete and in the staging area by Sunday, at 6 de l'après-midi. That meant it had to leave the fabrication shop by Sunday at 2 de l'après-midi. That meant final welding had to be complete by Sunday noon. That meant the section had to be in the jig by Saturday at 6 de l'après-midi. That meant all components had to be ready by Saturday at noon. Henderson created detailed schedules for every section showing exactly when each step had to be completed. Workers followed these schedules religiously. If a section was behind schedule, resources were shifted to catch up. If a section was ahead of schedule, workers moved to sections that were behind. The goal was for all sections to arrive at the slipway exactly on time, not early, not late, exactly on time. This eliminated storage costs and space requirements. In traditional shipyards, partially completed components sat around for weeks waiting for installation. Henderson's yards had almost no work in process inventory. Sections were built and immediately assembled. The financial advantage was substantial, less. Inventory meant less capital tied up. Less storage space meant lower facility costs. Less time between fabrication and assembly meant higher quality because welds did not have time to corrode or degrade. The safety improvements from Henderson's methods were dramatic. Traditional shipbuilding was dangerous. Workers labored in cramped space, overhead positions, and poorly lit conditions. Falls, injuries, and accidents were common. Henderson's fabrication shops were safe by comparison. Workers built sections on the ground in well-lit open spaces. The most dangerous work, final assembly on the slipway, involved far fewer workers and far less time. Accident rates at Higgins yards using Henderson's methods were 40% lower than at traditional East Coast shipyards. Fewer accidents meant lower insurance costs, less downtime, and better worker morale. The cost savings from Henderson's prefabrication method were enormous. The Navy estimated that traditional construction of an LST required approximately 5,000 man-hours from keel laying to completion. Henderson's method reduced this to approximately 2,000 man-hours, a 60% reduction. Multiply that by 0.5 LSTs built during the war, and Henderson's system saved approximately 315 million man-hours compared to traditional construction. 315 million hours is 36,000 years. If one person worked 8 hours per day every day, it would take over 0.000 years to accumulate that much time. This time savings translated directly to cost savings. An LST built using traditional methods cost approximately $1 million. An LST built using Henderson's prefabrication methods cost approximately $1 million. The 7 cents dollars difference per ship, multiplied by 0.5 ships, totaled over $735 million in savings. In $1943. Adjusted for inflation, that would be over $12 billion in savings in today's currency. But the real value was not measured in money, it was measured in time. Ships in the water faster meant military operations could begin sooner. Delays in LST production delayed invasions. Invasions delayed meant more time for enemies to prepare defense. More time for enemies to prepare meant more Allied casualties. Henderson's prefabrication system did not just save money. It saved lives by enabling faster military action. The impact extended beyond LSTs. Henderson's methods were adapted for other ship types. Destroyer escorts used prefabrication extensively. Liberty ships incorporated prefabrication principles. Even aircraft carriers used prefabricated sections for certain components. The entire American shipbuilding industry was transformed by techniques Henderson pioneered on LST construction. After the war, Henderson's prefabrication methods became standard practice in commercial shipbuilding worldwide. Modern shipyards in Japan, Korea, and China build enormous container ships using principles Henderson established. Ships are divided into large sections. Sections are prefabricated in workshops. Sections are assembled using cranes. The processes are more automated now. Computer-controlled cutting replaces templates. Robotic welding replaces manual welding. But the fundamental approach remains the same. Build the pieces first, then assemble the ship. Henderson retired in 1946, returning to pipeline welding in Louisiana. He worked another 15 years in the oil industry, then retired to a small farm outside Baton Rouge. He rarely spoke about his wartime work. When asked, he would shrug and say it was just welding, nothing special. His family did not learn the full extent of his contributions until after his death in 1979. A nephew researching family history discovered documents showing Henderson's role in LST production. The nephew contacted naval historians who confirmed that Henderson's prefabrication system had been critical to Allied victory. The Navy had never officially recognized Henderson's contribution. His name appeared on no awards, no citations, no monuments. He was one of thousands of civilian workers who contributed to the war effort and then disappeared into obscurity. But his impact was undeniable. The zero-sink LSTs built using his methods carried millions of tons of cargo, thousands of vehicles, and hundreds of thousands of troops onto hostile shores. Without these ships, D-Day would have been impossible. Without these ships, the island-hopping campaign in the Pacific would have taken years longer. Without these ships, the war would have lasted longer and cost more lives. The story of Henderson's prefabrication revolution extends far beyond the statistics of man-hours saved and ships built. It represents a fundamental shift in how America approached industrial challenges during the war. The traditional shipbuilding establishment believed that quality required time, that speed meant cutting corners, that rapid production inevitably resulted in inferior products. Henderson proved them completely wrong. His LSTs were not just faster to build, they were better. The structural integrity of prefabricated LSTs exceeded traditionally built vessels. Navy inspectors documented this repeatedly. Welds performed in Henderson's fabrication shops, where welders worked in optimal conditions with proper lighting and comfortable positions, were consistently higher quality than welds performed in cramped ship interiors. The dimensional accuracy of prefabricated sections, built in precision jigs, exceeded the accuracy achievable through traditional measurement and fitting methods. Several traditionally built LSTs experienced structural problems during their service life, including cracked welds, misaligned bulkheads, and leaking compartments. These problems were virtually absent in Henderson's prefabricated ships. The reason was simple. Better working conditions produced better work. The lesson should have been obvious, but it took a war emergency to force the shipbuilding industry to learn it. The operational history of LSTs built using Henderson's methods validated his approach. These ships served in every theatre of war. They crossed the Atlantic in winter storms. They navigated coral reefs in the Pacific. They survived German artillery at Normandy. They withstood Japanese kamikaze attacks at Okinawa. They proved to be tough, reliable, and capable. Many remained in service long after the war ended. The United States Navy operated LSTs through the Korean War and into the Vietnam War. Some Henderson-built LSTs served 20 years or more. Several were transferred to Allied navies and served even longer. The last World War II-era LST in American service, USS LST 321, was decommissioned in 1946, but later transferred to the Greek Navy, where it served until 1999. A group of LST veterans purchased the ship and sailed it across the Atlantic to the United States for preservation as a museum ship. LST 325 now sits in Evansville, Indiana, exactly where it was built in 1943, using Henderson's prefabrication system. Oversent 000 visitors tour the ship annually. Walking through the compartments, visitors can see evidence of Henderson's modular construction. The alignment marks where sections joined are still visible. The quality of the Hute 0-year-old welds is remarkable. Naval architects who examine the ship are consistently impressed by the engineering sophistication of the prefabrication design. The influence of Henderson's work extended into the Cold War era. When the United States needed to rapidly expand its fleet during the Korean War, the Navy turned to prefabrication methods refined from Henderson's LST techniques. Destroyer escorts, minesweepers, and patrol craft were built using modular construction. The principles remained the same even as the technology evolved, but perhaps Henderson's most significant legacy was demonstrating that innovation could come from unexpected sources, and that established expertise could be wrong. The naval architects who dismissed prefabrication as impractical were not incompetent. They were experienced professionals who understood traditional shipbuilding deeply. Their mistake was assuming that what had always been done was the only way to do it. Henderson had no formal engineering education. He never attended naval architecture school. He never designed ships before the war. His expertise was welding and fabrication, not shipbuilding. But that outsider perspective allowed him to see solutions that insiders missed. He was not constrained by assumptions about how ships must be built. He approached the problem fresh, without preconceptions. This pattern appears repeatedly in the history of innovation. Outsiders revolutionize industries because they do not know what is supposed to be impossible. The Wright brothers were bicycle mechanics, not aeronautical engineers. Steve Jobs was a college dropout, not a computer scientist. Elon Musk was a software entrepreneur, not a rocket scientist. Each brought fresh thinking to established industries. Each was told their ideas would not work. Each proved the experts wrong. Henderson fits this pattern perfectly. The organizational lessons from Henderson's work are equally important. His success depended on more than just technical innovation. It required a complete rethinking of how work was organized, how workers were trained, how quality was controlled, and how production was scheduled. Modern manufacturing terms like lean production, just-in-time delivery, and continuous improvement all describe principles Henderson implemented in 1942. He did not use those terms. The formal theories did not exist yet. He simply observed what worked and did more of it. The business school professors and management consultants came later, formalizing and teaching principles that practical innovators like Henderson had already discovered through experimentation. The economic impact of Henderson's prefabrication system extended beyond direct cost savings. By enabling faster LST production, Henderson's methods allowed America to pursue military strategies that would have been otherwise impossible. The decision to invade Normandy in June 1944, rather than later in 1944 or in 1945, was directly influenced by LST availability. Each month of delay would have given Germany more time to strengthen Atlantic Wall defenses and would have given the Soviet Union more time to advance into Eastern Europe. The earlier invasion date, made possible by Henderson's production system, shaped the post-war map of Europe. In the Pacific, LST availability determined the pace of the island-hopping campaign. Admiral Nimitz's strategy of bypassing strongly defended islands and attacking weaker points depended entirely on having enough landing craft to maintain operational tempo. Japanese commanders repeatedly noted in after-action reports that American amphibious capability was the decisive factor allowing rapid advances across the Pacific. The availability of Henderson's prefabricated LSTs, arriving at forward bases faster than expected, kept Japanese forces off balance and unable to concentrate defense. The broader lesson about industrial capacity as a weapon of war cannot be overstated. Germany and Japan both fielded technologically sophisticated weapons and tactically proficient forces. But they lost because they could not match American industrial output. Henderson's contribution to that industrial superiority was significant. His prefabrication system was one of hundreds of innovations that collectively gave America overwhelming material advantage. The Germans built excellent tanks, but America built 5 times as many adequate tanks. The Japanese built superb aircraft carriers, but America built D times as many good carriers. Quality mattered, but quantity mattered more. Henderson's methods delivered quantity without sacrificing quality, the ideal combination. After the war, American industry maintained its dominance for decades, partly due to manufacturing techniques developed during the war years. The lessons learned from Henderson and other innovators spread throughout American business. Prefabrication, modular construction, standardization, and parallel production became standard practice in construction, manufacturing, and assembly. The post-war economic boom was built on wartime innovations commercialized for civilian use. However, America did not maintain its lead forever. By the 1970 secondes and 1980 secondes, Japanese manufacturers were outcompeting American companies in automobiles, electronics, and other industries. The Japanese success was often attributed to new management techniques like just-in-time production and total quality management. But these techniques were not new. They were refinements of principles American innovators like Henderson had pioneered decades earlier. America had forgotten its own lessons. Companies grew complacent. Managers focused on short-term profits rather than long-term innovation. Workers became disconnected from quality. The entrepreneurial spirit that drove wartime innovation faded in peacetime bureaucracy. The revival of American manufacturing in recent decades has involved relearning principles Henderson understood in 1942. Modern factories emphasize worker empowerment, continuous improvement, and elimination of waste, exactly the principles Henderson applied to LST construction. The current reshoring movement, bringing manufacturing back to America from overseas, faces challenges Henderson would recognize. How do you rapidly train workers for specialized tasks? How do you organize production for maximum efficiency? How do you maintain quality while increasing speed? Henderson's answers, standardization, modularization, jig-based precision, and workflow optimization, remain relevant 80 years later. The personal story of Marcus Henderson also offers lessons about recognition and reward. Henderson received no fame, no fortune, no public acknowledgement for his contribution. He returned to modest work, lived a quiet life, and died in obscurity. This seems unjust. A man who helped save thousands of lives and shortened the war by months should have been celebrated. But Henderson never sought recognition. He saw a problem. He solved it. He moved on. This attitude was common among his generation. The World War II generation accomplished extraordinary things without demanding personal credit. They understood themselves as part of a collective effort. Individual glory was less important than collective success. Modern culture emphasizes personal branding, individual achievement, and public recognition. Henderson's anonymity seems strange by contemporary standards, but perhaps his approach was healthier. He found satisfaction in work well done, not in public praise. He measured success by results, not by recognition. He lived according to his values without needing external validation. There is dignity in that approach that our celebrity-obsessed culture has largely lost. The technical documentation of Henderson's prefabrication system, preserved in national archives and naval records, continue to influence modern shipbuilding. Naval architects studying efficient construction methods examine Henderson's designs, the modular section sizes, the jig specifications, the assembly sequences, all remain relevant. Some modern shipyards use construction methods remarkably similar to what Henderson developed in 1942. Computer-aided design and robotics have enhanced the process. But the fundamental approach of building modules separately, then rapidly assembling them, remains the same. The environmental implications of Henderson's methods are also worth noting. Faster construction with less waste meant fewer resources consumed per ship. The elimination of rework and error correction reduced material waste. The efficiency improvements meant less energy consumed in manufacturing. In an era before environmental consciousness, Henderson accidentally created a greener shipbuilding process simply by pursuing efficiency. This demonstrates an important principle. Efficiency and sustainability often align. Waste is waste, whether you care about it for economic reasons or environmental reasons. Methods that eliminate waste serve both purposes. The human cost of Henderson's achievement should not be forgotten. His workers labored in grueling conditions. The fabrication shops were hot in summer, cold in winter. The work was physically demanding. Injuries occurred despite safety improvements. Workers put in 60 to 70-hour weeks for months on end. They did this because they understood the stakes. Every LST they built would carry American soldiers into battle. Speed literally meant saving lives. Many of Henderson's workers were women. As men joined the military, women filled factory jobs in unprecedented numbers. The prefabrication system was ideal for female workers. It did not require heavy lifting because cranes moved large sections. It did not require years of apprenticeship because jigs eliminated complex measurements. Women proved to be excellent welders, often more meticulous and careful than their male counterparts. Henderson recognized this and actively recruited female workers. By 1944, over 40% of his fabrication shop workers were women. Several became shop supervisors, leading teams of 20 or more workers. After the war, most of these women were pushed out of factory work as returning soldiers reclaimed jobs. This was a tragic waste of talent and experience. Many of the women Henderson trained were bitter about being forced out of work they did well and enjoyed. One woman, Ruth Martinez, who had supervised a tank deck fabrication team, wrote a letter to Andrew Jackson Higgins in 1946 protesting her layoff. Mr. Higgins, for 3 years I built ships that helped win the war. I was good at my job. I took pride in my work. Now I am told I must leave because the men are back. This is not fair. I want to keep working. Higgins wrote back a sympathetic but ultimately dismissive reply. The war is over. Times are different now. You should be proud of your service. Your country thanks you. Martinez never worked in manufacturing again. She spent the rest of her working life as a secretary, a job that paid half what she had earned as a welding supervisor. Her story was repeated thousands of times. The technical skills women developed during the war were discarded. Society's loss was incalculable. The counterfactual question of what would have happened without Henderson's innovation is worth considering. If LSTs had been built using traditional methods, requiring dis-to-dos months per ship, American shipyards would have completed perhaps 300 to 400 LSTs by mid-1944 instead of the 800 actually available. With 400 fewer LSTs, the D-Day invasion would have been delayed until late 1944 or early 1945. German forces would have had additional months to strengthen defences. Welder rocket attacks on Britain would have intensified. The Eastern Front would have Welder rocket attacks on Britain developed differently with Soviet forces advancing further west before the Second Front opened. In the Pacific, with fewer LSTs, the island-hopping campaign would have advanced more slowly. Islands like Saipan, Guam, and Iwo Jima might not have been taken until 1946. The bombing campaign against Japan would have been delayed. The war would likely have continued into 1946, possibly requiring the planned invasion of Japan's home islands. Casualties would have been catastrophic on both sides. Henderson's prefabrication system, by accelerating LST production, arguably saved tens of thousands of lives and shortened the war by 6 months or more. That is the true measure of his achievement. The final irony of Henderson's story is that his methods, which seemed radical and risky in 1942, became so completely accepted that within a few years they seemed obvious. By 1950, no one remembered that prefabrication had once been considered impossible. It was simply how modern ships were built. Henderson's revolution became so successful that it erased memory of what it had revolutionized. This is perhaps the highest compliment, an innovation so effective that it stops seeming innovative and becomes the new normal. Today, when someone proposes a new construction method, a new manufacturing process, or a new organizational structure, they face skepticism, similar to what Henderson encountered. Experts explain why it will not work. Established practices are defended, change is resisted. But occasionally, the new idea actually works better than the old way. Occasionally, the outsider perspective reveals solutions the experts missed. Occasionally, the impossible turns out to be merely difficult. Marcus Henderson proved that the impossible assembly of a 328-foot ship in 72 hours from prefabricated sections could actually be done. He proved it not with arguments or presentations, but by doing it. He built the sections. He assembled the ships. He launched them into the water. Results speak for themselves. That is perhaps the most important lesson of his story. When everyone says something cannot be done, there are two possibilities. Either they are right, or they lack imagination. The only way to find out which is to try. Henderson tried. He succeeded. And thousands of young men came home from war because ships reached the battle zones faster than enemies expected. That legacy, even if largely forgotten, was worth every hour Henderson spent building jigs, training workers, and proving that the impossible was actually possible all along.